Hi, I'm Rachel, and I'm joined by my co-authors Aiden, Francisco, and Starlika. We're excited to present our research project, Forecasting West Nile virus infections, a machine learning approach to epidemiological monitoring.
We have a problem. Mosquitoes are vectors for a number of serious illnesses, one of which is West Nile virus. In the United States, West Nile virus is the leading mosquito-borne disease. As there are currently no vaccines to prevent West Nile virus, nor medications to cure it, government agencies must sustain financially taxing programs to monitor mosquito populations and West Nile virus infections in an effort to prevent West Nile virus outbreaks. In our study, we provide a solution. 4 machine learning models that forecast West Nile virus infections in humans, enabling government and healthcare officials to take proactive action instead of reacting to real-time infection data.
Our research approach is informed by and builds on prior literature. We began by reviewing machine learning models that were successfully applied to mosquito prediction tasks. Support vector machines and random forest regressors emerged two of the strongest options. Then, we analyzed prior work's feature selection and found that they predominantly relied on ecological variables for model input, as environmental factors drive mosquito population and vector dynamics. We used the correlations found between various papers' ecological input and mosquito output to select the input for our models.
These findings guided our methodology. We used Globe citizen science data to select and analyze our area of interest. We began by plotting Globe mosquito habitat mapper data using ArcGIS. In doing so, we found that Los Angeles, Riverside, and Orange counties had a significant amount of Globe data. The consistent Globe data available in these areas, despite the opportunistic nature of citizen science data collection, demonstrates the significant impact of the local mosquito population on the community. The Californian government also provides ample data on West Nile virus infections in these counties. Furthermore, the Globe land cover observations in our AOI revealed variable vegetation throughout the mosquito season, providing ecological patterns we could use to predict West Nile virus infections.
We decided to include humidity, temperature, precipitation, wind speed, AQI, and EVI in our ecological input. We averaged this daily data into weekly data that aligns with the CDC's MMWR epidemiological week structure. We padded missing values in our time series using means calculated across each year's mosquito season.
Previous studies emphasized the importance of time lag. We also implemented a time lag in our data by graphing our ecological variables and West Nile infections, then shifting the ecological variables forward to align them better with the West Nile virus data. We tested various time lags and found 5 weeks to be the optimal value.
We trained 3 support vector machine regressors and 1 random forest regressor. Here's what we found. Keeping in mind the RF and SVM work on different scales when we look at overall RMSE, the RF regressor clearly displays stronger performance than the SVMs. However, when looking at MAE, the 4 models display rather similar performance, with the RBF SVM ultimately outperforming all other models. This variation is likely a result of the nature of the error metrics MAE and RMSE. MAE is linear in nature, therefore it penalizes all errors equally, while RMSE is nonlinear and weights errors that are larger in absolute value more heavily. With this understanding of our error metrics, we can conclude that the RF regressor is indeed stronger than the SVMs, as it is less likely to produce an error that is large in magnitude. Here is our random forest feature importance. Temperature emerges as the most important feature and precipitation as the least important, while EVI, AQI, wind speed, and humidity are all of similar importance. So, to recap our findings, random forest regressors proved to be most well suited to our prediction task. However, they had a strong counterpart in the RBF support vector machine regressor. Our results show that not only are AQI and wind speed non-negligible in their importance, they are also almost as important as EVI, which is a measure of vegetation, and humidity, both of which are well known to be critical for predicting various mosquito characteristics. Our methodology and results hold valuable insight for the development of early warning systems that aid healthcare and government officials in preparing for and preventing incoming West Nile virus outbreaks. Our predictions are particularly valuable when assessed from a resource allocation standpoint, as the 5-week lead time they provide can aid healthcare providers in predicting when they must increase capacity. This early notice is critical to avoiding preventable deaths.
A big thank you to Dr. Lowe, Ms. Sofing, Mr. Nelson, Dr. Podest, Andrew Clark, and Juliana Schneider for their support.